Bismillahirrahmanirrahim. In this video, I will discuss the investigation and optimization of a plasma arc cutting process of a stainless steel material AISI 304 by integrating Principal Component Analysis and Composite Desirability Method. In this research work, the plasma arc cutting machine is used to cut the stainless steel material in the square shapes. This is the picture of the plasma arc cutting machine. I have taken 4 factors: arc current, voltage, cutting speed, torch height, and 3 levels of each parameter. So based on the information provided in the table number 2 about the parameters, I will make such a table of the Taguchi design. So in the Minitab software, click on Stat, then click on DOE, then Taguchi, create a Taguchi design. Here we have 4 different factors. Each of them has 3 levels. Click on Design, on L27, then factor, write out the name of all the factors. So I input all of the name of the factors. First of all, I will make a coded design in which instead of having real factors of the values, we will use coded values just like 1, 2, 3 for each of the level. Click OK, then click Options, save the design in the sheet, click OK, and then OK. So you got such a design, you can view it. So we have 27 number of experiments because it's a L27 design. After that, if you want to make an uncoded design, again go to Stat, DOE, Taguchi, create a Taguchi design, and then factors. Here in front of the factor, just input the levels. It's quite easy, just like Excel, 160, 170, then space and 180. Likewise, for the cutting speed, it will be 1300, 14 and 1500. So in order to save the time, 1300, 1400 and 1500. I'm pausing the video. So all of the information has been entered. Click OK and then OK. So you got the uncoded design, but it will be in another sheet. Then you will have to write the name of the response variables. So I have entered the values of 6 response variables. I have RA, RQ and RZ. These are the surface roughness profile parameters, and then curve width, draws, and material removal rate. Each of them has been explained in my research paper. In order to analyze, so first of all, we do the signal to noise ratio analysis. So click on Stat, DOE, Taguchi, and then Analyze Taguchi design. This time, first of all, I want to analyze RA. For the RA, I need the graph, only 2 signal to noise ratio and the mean. These are required for the research paper. Analysis, I need signal to noise ratio and response, the response table for these 2. Yes, these are also required for the research paper. Terms, nothing to do with them because all of the 4 terms are already included. Then click on Options. So smaller the better. Why? Because we need the surface roughness to be as less as possible. In the storage, we need signal to noise ratios only, nothing else. Click OK and then OK. So you will get a new column here. You can see it here. It's a new column of signal to noise ratio for the RA. So question arises, why the 2 values are missing? Because if we go to the formula of signal to noise ratio, so you can see it here, A. The A is the number of replication, and in L27, each of the treatment has been replicated twice. What is meant by this? Now you can see it here, the 1, 2, 3. These 3 are the same, are run at the same setting. These are the same treatment, 1, 1, 1, 1. So like this, if you pick 10, 2, 1, 2, 3. So 2, 1, the next 2 also will be 2, 1, 2, 3. I hope you got my point. So how many the replications will be? You will get only 1 signal to noise ratio value for all of the treatments that are similar. To save the time, I am doing the analysis at a very fast rate. So view it and then click OK. You will get for the RQ. Then follow the similar step in order to do it for the RZ. Click OK. So you are look at there, the columns are being generated. I have done the computation for the 5 signal to noise ratio because there the criteria was smaller the better. Now for the MRR, material removal rate, the criteria will be larger the better or higher the better. So you will just have to click the options button here, select larger is the better, Nothing else to do. Click OK and then OK. So you will get 6 signal to noise ratio values. One thing more, the signal to noise ratio value will remain same either you do the analysis using the coded design or uncoded design. Now you can do the analysis based on two things, on the original data of the responses or on the signal to noise ratio. It's up to you. The results are valid for both of them. However, I did the analysis on the original values. How we can do the normalization? So these are the formulas. Pij, it's the individual value minus maximum of the Pij. So it is the maximum of all this RA column value, that is I have 931.52 in this case, divided by maximum value, again 931 minus minimum of the Pij. So minimum is, I think it's 192.18. So you can see it here, the formula, and then after that take the power. So in this case, the most usually the power or exponent, it is taken as 1. So in this way, you will have to compute the normalized data. This normalized data has been used further. So do this normalization. I think it's easy, or I have made a separate video on all the parts of this research paper. So you can have a look at my channel and you can watch it. Once you have done with the normalization, copy this whole data and then paste it in the Minitab software. In the Minitab, you will have to now do the principal component analysis to extract the weights. Why we are extracting the weights? Because the various contribution by each of the response variable is different. So again, go to stat, then go to times multivariate principal components. Select all of the variables here. Select all of them. Then type of matrix is correlation. Click on graphs. Nothing else to do. If you want to need a script plot, it's okay. Otherwise, no need. Storage, it's all okay. Nothing else to do. Click OK. So you will get such a result. Now, what is meant by these? So here you can see that we have 6 response variables. So there are 6 principal components. This proportion is the variance contribution by each of the principal component. So you can see that 66.4% variation has been explained by the PC1, and so it's a very good amount of variation has been explained by this principal component. So we will select the principal component associated with our PC1, principal component number 1. So copy this whole table and paste it in the Excel. You can copy it in the form of you can see it here, just make copy and then paste it here in the Excel. There we go. So now what we will have to do, using the principal component number 1, we will have to extract the weights because their sum isn't equal to 1. So now you will have to take scale of each of the value. How you can do it? For example, it's C27. So I took this scale of C27 to get the weight of RA. So you can see it here, C21 multiplied by C27. So I got 0.23. Like, if you take the sum of all these weight, it should be equal to 1 while you are doing the calculations. So it's 0.99, roughly equal to 1. Now you can use these weights for the multiple objective optimization. Now, how you can do it? Just copy these weights from here and paste them with the data of the normalized. Now you will have to compute, since all of this data is associated with the treatments. So for the treatment number 1 or 1, 2, 3 that are similar, so we will have to calculate a desirability value for each of the treatment. How you can do it? So you will do it in such a way that multiply this first cell of, I'm talking about this one. So multiply this first cell with the weight of the RA. This second cell I am highlighting in the orange, 0.395 with 0.235. In this way you will do. For example, is 373. So it's the weight of the RZI. Hopefully you got my point now, that it will be multiplied by 0.224. So in this way, let me highlight in the yellow color so that my viewers will get my point. And similarly, this dross will be multiplied again it will be multiplied with this weight yellow color. Okay, so you can view the formula here that J6, so J6 is 0.411 multiply P6, it has been fixed, so 0.23. Then again multiply by K6, so K is 0.395, so you will have to multiply the value with weight, again multiply with the value and the weight, a respective weight, multiply value with the respective weight 0.224, likewise multiply all of them. So since one of the value of the MRR here is 0, so you got the multiplication result equal to 0. Then you will have to multiply the values of the second row with these weights. Again you will get some result. In this way you will multiply all of them, like 1 multiplied by 0.234. Sorry, here you can see there is the formula J14, the last value, so multiply by P6. So what you will do, this 1 multiply by 0.234, then 1 multiply by 0.235, 1 multiply by 0.224, so you got this value. Now the next thing is the ranking. So ranking means that which of the treatment has the highest desirability value. So it is quite obvious that the last treatment has the highest. However, you can rank it by using the formula of the ranking. So here's the formula. You will have to write rank, then R6, select the cell based upon which you want to do the ranking, then comma, then R6 to R14. Please insert the dollar symbols here. The whole column should be selected and just drag it down, so you will get all of the values. So I got the highest value at the treatment number 9. So it means that the treatment number 9 is the best one. Is it over multiple objective optimization results? No. So what should we have to do now? Here is the tricky point come in this research work. So what you will have to do, you will have to again go to stat, DOE, Taguchi, create a Taguchi design. Yes. Again, we have 4 number of factors. Select L9 because now you have 9 observations. Click OK. Okay, you will get a design. And then in front of the design, click here design only and paste all of the values here. After pasting the data, again go to stat, DOE, Taguchi, analyze Taguchi design, select the response option. Here select larger is the better because you want to maximize the value of the desirability function. You will have to select the highest value. Click OK is the result. So this is our output or claim of the research. Now what is meant by this? The delta. Delta has been computed by subtracting the lowest mean. What is meant by this? It can be depicted as the lowest value of the desirability is at level 1 of C and the highest value is obtained at the level 2 of the C. C is the current. Whereas the difference between these two is 0.4181. Likewise, the difference between the voltage value at level 1 and level 3. So these are the lowest and the highest. Their difference is 0.5161. You can see it here, the least desirability is obtained at level 3 of the temperature and the highest value is level 1 of the temperature. So we got a delta values computed. So you can see it here, the highest delta values rank is 1. So it means that the current has the highest effect in the plasma are cutting, followed by the temperature, then speed, and then voltage. Now what is the multiple optimization here? So you can see it here. We can say that C2, the second level 2 of the current, level 3 of the voltage, level 2 of the speed, and level 1 of the temperature is found to be over multiple objective optimization. Furthermore, I want to explain few things in this research paper. First thing is about signal to noise ratio. How I have selected this mono optimization, since the signal to noise ratio only optimize one of the response at a time. So you will have to select the highest value. So in this we have the highest value is 45.67. So a reference to this number 9, experiment number 9, or experiment number you can see 25, 26, 27, it will be 3321. So you can see it here, 3, 3, 2, 1. These are the setting. These are found to be optimal for the RA. The optimal setting for RA, RQ and RZ are same. However, if you see it here, it is C3V1 S3T2. Or you can see it here, the treatment number 7. So we will go there and we check that which of the treatment number is this, because we have done 3 treatments. So please remember 3132. So these treatments are the optimal for MRR. Likewise C1V1ST. So you can see the first treatment number 1, 2 and 3. These are optimal for the curve fit. We are now left with table number 4 ANOVA results. Let me do it. So you can perform the ANOVA in 2 ways. I am doing both. Go to stat, in regression, then regression, fit regression model. Select your response variable. My response here is RA, continuous predictors from R current till torch height. Select all of them and then initially nothing else to click OK. You will get the regression results. However, if you got some issues, then you have a lot of the ways to tackle it. However, in this case, I have arc current, arc voltage and torch height are found to be significant because their p-value is less than 0.05. The cutting speed is found to be insignificant on the RA. Similarly, you can repeat the same steps for the rest of the responses. Just you will have to replace this RA with the next variable, that is RQ. So in this way, you will have to repeat 6 times the analysis to get the result. Just click OK. The second method here is that go to again the similar step, stat, regression, then regression, fit regression. Here go to stepwise. In the stepwise, you have a lot of the option: forward selection, backward, forward information criteria. Then you have different information criterias, AIC and then Bayesian. So you can apply or try these to get the result if the simple regression is not giving you the desired or the best results. So this is one of the method. And the last method of this video, go to stat and then go to ANOVA. You go to GLM, fit the GLM, select your response variable, select the factors from current to torch height, select all of them in the factors, nothing else to do. Again, click OK. Initially check whether if you're getting the result, it's okay. If you're facing some issues, then okay. You can see it here that all of them are found to be significant. So in my research work, either use the GLM or use the regression. Both of them are okay. Thanks a lot for watching such a lengthy video. Bye.